Hello everybody, my name is Kevin Gomez. So I'd like to start off with just making an observation that many of you probably already know, and that is that traits have genetic variation, right? It's very important. And in particular, if we look at life history traits, what we find is that they tend to have lots of genetic variation. And that's actually very surprising, right? Given their connection to fitness. So, it's something that people have looked at. And one explanation for why this may be the case has to do with the fact that often we observe negative genetic correlations between these kinds of traits, right? And in the case, for example, here for this study with Drosophila melanogaster, sorry, mathematician. In the case of that organism, just looking at two traits, for example, we can see that this distribution of points is elongated along the direction of a line that has negative slope, right? Which indicates the negative genetic correlation. So the importance of this is that if we consider, for example, this line representing the trade-off between the underlying trade-off between these two traits, then what happens is that the shape of this distribution being this way means that basically what matters is variation along the perpendicular direction. That's basically what selection sees, what selection acts upon. And so what this results in is that when we look at individual traits and we measure the variance in these traits one at a time, so for example here if we look at longevity, what we'll find is exactly large variances, but in reality we actually have smaller variances that are relevant to selection, right? And so this basic shape of the distribution can explain the observations that we see for life history traits. So we know that from this, negative genetic correlations can play an important role in kind of explaining these observations. But in general, they also have a very big impact in terms of shaping the evolution of traits under natural selection. And so that's clearly expressed in what is known as Lambda's equation, which I've included here for two traits. And what this equation tells us, basically, is, for example, if we focus on the first trait here, the change in the population mean of trait 1 is going to be given by the amount of additive genetic variance in that trait multiplied by the amount of selection in that trait plus the genetic covariance multiplied by the amount of selection in the second trait. And so the significance of that is that if we have negative genetic correlation between the two traits, that also means that we have negative genetic covariance. And so if there's any selection in the second trait, because this is negative, we'll actually have a reduced amount of change in the first trait, right? So in this case, we know that basically the genetic covariances or genetic correlations are important in shaping the short-term evolution of traits, right? And if we want to ask questions about, how traits evolve together, we need to basically look at this picture and more importantly note that these components here are responsible for shaping the short-term evolution, but we also need to account for the fact that these components as well change in the long term and are shaped by forces in evolution, right? And so basically if we want to investigate questions regarding how traits evolve together, we need to be able to say something about how this matrix here, which is known as the G matrix, changes over time. So that's kind of like our starting point. And so the basic idea is that if we go out and look at genetic correlations, most often at the level of population genetics, which basically means that we're looking at loci, alleles at those loci, most often the genetic correlations are due to underlying trade-offs which indicate antagonistic pleiotropy, right? That's pretty much the basic explanation for a lot of what we see in terms of these traits being related the way that they are. But alternatively, we also have linkage disequilibrium as a possible source of genetic correlations, right? And so the idea is that, unfortunately, basically the influence of linkage disequilibrium on the dynamics of the G matrix, which is important to answer questions about the long-term evolution of traits, hasn't been investigated as much as, in the case for pleiotropy, which, there are models that tell us a little bit about, how that G matrix changes and can answer questions about trait evolution over time. So this is kind of what we're interested here and what we've been working on, is looking at linkage disequilibrium, its effects on the G matrix, the dynamics of the G matrix, and how that inevitably results in the in evolution of like traits together. So we're going to take we took a modeling approach to answer this question, trying to investigate this question. And so naturally what we did is focused on asexuals. You know, this is where linkage really matters in these groups. And then we also kind of considered the simplest case where we're just looking at 2 traits, right? And each of the traits contribute to fitness equally. And more importantly, we're trying to really understand what linkage disequilibrium's role is in shaping the dynamics of the G matrix. And so we excluded this idea of no plyotrops. What that means is that we're considering a model in which we have 2 traits, each controlled by separate loci that evolve independently. So as a starting point, what we did is we kind of looked at an existing model for asexuals, which is a very good model, and it allows us to kind of, a starting point to kind of explain what these variances might do over time as a result of linkage disequilibrium. And so basically what the model consists of is, so again, we're looking at asexuals, and what we look at is the distribution of fitness, and then what we want to know is how this distribution changes over time. And the 2 primary forces that are kind of at work here are selection, right? And so what selection does is that it's decreasing the abundances of these less fit individuals and increasing the abundances of these fitter classes here. And so what happens is that this results in a kind of a contraction of this distribution's width, right? And then the other process that's kind of at work here is beneficial mutations. And so when beneficial mutations occur on the fittest background, we have an introduction of a fitter class that's now widening that distribution. So some of you may be familiar with this model, it's actually very popular. So. Ultimately, the action of these 2 processes result in this distribution shifting over time towards the right. And the rate at which it shifts is exactly the rate of adaptation. And that can be solved for in terms of the population parameters, or it has been solved for in terms of the population parameters. Now, the interesting thing is that, well, because in this particular model we can apply Fisher's fundamental theorem, we know that the rate of adaptation is exactly the variance here. So what you can imagine then is that we can visualize this axis representing evolution in just 1 trait, right? And so if we know something about how selection works, or the strength of selection, and the beneficial mutation rate and population size, we can know what the variance in fitness will be with respect to that trait. So this is kind of our starting point, and what we did is we now consider a distribution over a 2-dimensional trait space, right? So this distribution is kind of shown here. We've added the second axis here representing the second trait, and we have basically the same mechanisms at work. We have beneficial mutations that are kind of either affecting trait 1 or trait 2 and improve fitness when they occur on these classes here. And then we also have selection reducing the abundances of the less fit groups and increasing the abundances of the fitter groups. And so in our model, what we did is we took what we're looking at is a symmetric model. In other words, the parameters for mutation and selection are identical in each of these axes. And just as a starting point, because in fact this actually tends to be give really complicated behavior even in that case. So what we did is looked at that, a symmetric case. And so the important thing is that we can actually relate some of this model back to the 1-dimensional case here. So even though we have 2 axes representing 2 traits, what we can do is relate that to the single 1-dimensional distribution, right? By noting that if you have mutations, because we're assuming symmetry, if you have mutations occurring in one direction versus another direction, they both give you the same amount of fitness. So you have these lines of constant fitness, right? And so along the perpendicular line, the total fitness is increasing for these different classes. And so what we can do is basically collapse this distribution by grouping all of the identically fit classes into one kind of bucket here, or one group, and we recover the exact same dynamics of the 1-dimensional distribution. So that's kind of the model in essence, and what we found is that the distributions that emerge from this model are basically shaped in this way. We have negative covariance, as a result of kind of the basic assumptions. And so the distribution will be shaped in this way. And again, if you recall, selection really acts on the variation in this direction, and all of this variation is practically very neutral. In other words, it just exists, and until selection acts on the next fitter and fitter group, or as selection is eliminating the variance in this direction, it eliminates the variance in this direction, but it's much slower, so it persists. So now getting to the question of how do we just figure out the rate of adaptation in one trait, if ultimately that's what we're interested in. How does one trait evolve when we've added the second trait? And so we again appeal to Lambda's equation, and what we know is that the rate of adaptation in the first trait is going to be separated into two components, one being the additive genetic variance of that trait, and the genetic covariance with the second trait. So that's ultimately what's kind of driving the adaptation in a single trait. In other words, the progression of this projected distribution in that direction. So this problem is actually very complicated. This front here, stochastically, is pretty erratic, and although you can solve for some mean behavior, it still ends up being quite difficult to do so, to get at least solid results. So we're trying. But what we did is looked at simulations and tried to kind of figure out what the general behavior of this distribution is over time. And so here, this is kind of roughly what the parameters that, for the results that I'm going to show now, these are the parameters we've used, and we've kind of looked at ranges that were feasible and realistic. And so what we did find is that adding the second trait reduces the rate of adaptation in the first, right, which is this drop here. And the reason that happens is that when we go out and run simulations, we observe the variance in the first trait here, and there's, of course, zero covariance. And so by adding the second trait, now you consider the evolution of this two-dimensional distribution, the covariance increases in magnitude. It's negative, but it's basically a 90% of the magnitude of the original variance. So it's a substantial increase decrease. And then you also have the variance in the first trait, which increases by a smaller amount. I mean, it's still a substantial amount, but it's not as much as this covariance term. So really what's driving this reduction is basically the negative covariance. So this is interesting because it agrees with the results that, the observations on life history traits, and it's all driven by linkage disequilibrium. So while, we've said something about how the trait's evolution is determined by the covariance and variance, and ultimately that's what the components of the G matrix is. Basically, the actual terms themselves change very dramatically over long periods of time. And so you can see that the variance in the trait and the covariance fluctuate substantially, and that's kind of shown here. So that tells us that the G matrix is actually very unstable over smaller scales of time. Large scales of time, and usually that time scale is determined by the time scale of beneficial mutation selection balance. So just in summary, we've kind of used this model which just is driven entirely by linkage, and it basically describes evolution of two traits, and we found that this model explains the observations that we kind of made in the beginning. And what we get is a reduction in the rate of adaptation of one trait, and we also know that the G matrix that kind of, as a result of linkage disequilibrium, is actually unstable over larger scales of time because of linkage. So I'd just like to thank my advisor and a postdoc that helped me out with this project, and of course the funding. So.
How do you think your model might change, or how do you think your results might change if you use a continuous distribution of observation? Instead of having discrete classes, make the tree distribution continuous?
Well, so just kind of considering what happens just with the discrete case, if you have different selection coefficients or different parameters in the two dimensions, you get stochasticity that's really hard to kind of pin down. So if you had, let's say, for example, a distribution of fitness effects and mutations that kind of vary in what they provide for selection coefficients, you would have a lot of stochasticity, but